Hello everybody. In this video we're going to start talking about the kinetic reactors in Aspen Plus. So in the previous videos we saw the ideal shape of the reactors and each one of them and how we can define each one of them, and we were talking about them as ideal reactors because we didn't mention anything about the kinetics of the reaction. We just mentioned that this is simple reactor. We define very simple information and get minimum amount of data out of it. So in this video, we're going to start the actual reactors, or talking about the actual reactors, which are the reactors that are the real type of reactors that we use in our engineering applications. And in this kind of reactors, we'll talk about the kinetics intensively, and this is going to be a big part of this topic. So before talking about the kinetics, I just want to quickly review the kinetic reactors and the reactors that we have and what kind of equations that we use to define or to define these types of reactors mathematically. I mean, so there are three types. There is the continuous stirred tank reactor, there is the plug flow reactor, and there is the batch reactor. So the first type is the continuous stirred tank reactor, and from the name you can understand how it works. It's a tank and it's continuously stirred, so it's kind of like a vessel that has a stir, and the feed enters the reactor with the flow rate and the concentration of the reactants and at temperature T, and the reaction takes place in the reactor, and then the product comes out. This reactor is based on some assumptions. The first is the perfect mixing, which means that I assume that it is mixed well so that all the parameters inside the reactor are homogeneous. So I have the concentration, the temperature, and everything is uniformly or equally uniformly in the reactor. So I don't have parts with different values in the reactor. The second part is that, or the second assumption is that the feed flow rate is small compared to the volume of the reactor, and this is a kind of an important point because the equations that we put are based on the assumption that the concentration in the reactor equals to the concentration of the product. And I assume that this does not change a lot the concentration in the reactor. It's like you have like a cup of water and you put it in the sea, so nothing will change. The salt concentration of the sea is not going to change because of this cup of water. So it's the same. I assume that this is small compared to this volume, so the concentration inside is constant, and this concentration and temperature does not or do not change the concentration and temperature in the reactor. Accordingly, we assume that the product that's coming out has the same concentration of the reactant in the reactor. And based on these assumptions, we can do the steady state equation that describes this system, which is the in minus out equals the consumption. So I have the flow rate multiplied by the concentration, which is the number of moles or the mass of the feed reactant, and this is the mass or the moles of the feed or the product reactant. So I have like 100 here, and I had here 30 coming out, so the difference is the reacted inside the reactor. So this is the R multiplied by V, which is the rate of reaction multiplied by the volume. This R is kind of very important term because this is the rate of reaction where we put the kinetic term, and the kinetics of the reaction are all plugged in this part, and this is gonna be the point in all the types of reactors. In all the reactors we will have this R term, and this R term is where we're gonna put all the kinetics. So in our case, we will assume, just here for the sake of demonstration, we'll assume a very simple rate of reaction, which is the first order kinetics, which is K multiplied by the C. And here we put C node because this is the reaction taking place here. So this is the rate of reaction is calculated based on the concentration here, not on the feed concentration. And then we can kind of rearrange the equation, and then we will end up with the term V over F, which is the tau. And this tau is the residence time, and it kind of represents the time that the reaction or the reactants spend in the reactor to do the reaction. So as this tau gets bigger, then the reactants will take more time, so the extent of reaction would be higher. So this is how we can rearrange the reaction equation, and this is how we can put the outlet concentration as a function of the inlet concentration. So this is for the CSTR. Usually CSTR is used for the liquid, or it's not usually, it's always used for liquid phases. You cannot use this for gas phase because it's stirred tank, so it has to have a liquid phase inside. So it's used for mainly or always for liquid phases. Of course, this equation is based on an assumption as well, which is that the feed flow rate is constant, or the feed and the product flow rate is constant. It's both are F. It's not Fi and F out. This again for simplicity. In many cases, you might have differences either because of the change in volume due to the temperature, or something is consumed or comes out as a gas phase. Then you would have the volume changing. So there are many reasons that may cause this, but in our case, just again for simplicity, we just want to demonstrate the model, not to go into like different cases or scenarios. The second type of reactors, oh, I'm sorry, I missed the point. The one more thing that we need to do is to do the energy balance equations. And this is kind of one thing that makes the kinetic reactors kind of tough to deal with, or require some work in computational calculations, which is that this is the mass balance equation, and there is another equation which is the energy balance equation, that I say that the enthalpy of the feed minus the enthalpy of the product equal the enthalpy consumed here, which is the R multiplied by the delta HR, which is the heat of reaction. And usually, in this case, you'd see that the term R is present in the energy balance equation, and in this case, you have to put the kinetics here and there. And in this case, you have to solve these two equations simultaneously. And in this case, it's kind of simple case compared to the next cases, because I'm dealing with algebraic equations, and in this case you can solve them simultaneously with any software without the need of doing integrations or numerical integration or stuff like that. But again, this is one thing that's important here, that you need to solve, especially for the reactions that are endothermic or exothermic reactions, then you have to take care of this. And it may include the term of cooling or heating if you need to do that. And the terms of cooling and heating may include the heat transfer calculations to do, if you have a coil inside, then you have to calculate Reynolds number, the heat transfer coefficient, and then to do the heat transfer calculations. So it's not an easy task to do. So this is one point that is important to keep in mind. I'm not saying this because we are going to do this manually, but just to appreciate what the software is doing. This is one important point to keep in mind. The plug flow reactor is the second type of reactors, and and as you see, it's kind of like a tubular reactor. It sometimes say it's called tubular reactor. And this tubular reactor, you have the feed coming or entering the reactor from one side, and then it goes inside the reactor and comes from the other side with the concentration and temperature of the output stream. In this case, the dealing mathematical manipulation or the mathematical representation of this reactor is going to be totally different from the CSTR. The CSTR kind of comes out the umbrella of what we call the lump parameter system. So I deal with this as a lump, as one piece that has concentration, that has temperature. It's always uniform in here. So I don't have any distribution of the parameter in the system. But in this case, you're dealing with a system that has the parameters changing continuously inside the reactor. So the reactors or the reactants go inside the reactor from here, and at each point the reaction proceeds, the concentration changes, the temperature changes, and maybe the pressure changes as well. So at each point there is a change in the parameters, and this change affects the next part, and then the next affects the next, and then so on until you reach the other part. So the way we dealt with the CSTR is not possible to be used here, because I have to put a mathematical equation that takes in mind or puts in mind that this is a distribution or distributed parameter system, not a lumped parameter system. And that's why we have to take, or we do take a small increment of the reactor here. And this is what we can do the balance equations on. But before we do the balance equation, let's talk about the assumptions that we have. So we assume that there is it's a pure plug flow. What I mean by plug flow, it's like when you have a syringe and you are pushing it, and when you push the syringe, the plug of the syringe is moving, or the head of the plug is moving uniformly. You don't have one part of it is going forward more than the others. So, and this is what I mean, that this part is moving as a whole to the forward or to the backward. So it's not there is no what's called axial dispersion. So I have this part is kind of small CSTR. It's perfectly mixed increment. It has uniform concentration, uniform temperature at all radii at the same height. Of course, it's different from here and it's different from there, but this is uniform at this part, at this DZ part. And the only parameter or the only independent variable is the position. So I have, of course, in the steady state operation, so I have no change in by dz. I mean by dt or by dr. So I have the r is not a parameter that here. So we take this part as the control volume that we do our equations on, and then we do the balance equations on this part. I assume that this is the C and T, the inlet conditions of the concentration and temperature, and there is an incremental or differential change in the concentration, which is dc, and differential change in temperature, which is dt. Of course, this is very thin part. It's not as wide as I show it here, but this is a very thin increment of the reactor. And then we do the balance equations the same way we did for the CSTR. So assume that this is a small CSTR and you're doing the calculations on the volume of this increment is the area multiplied by the width, which is area multiplied by dz. So what I'm gonna say is that the F multiplied by C plus dc minus the F multiplied by C, which is this term, which is the out minus in, equals again the r multiplied by dv in this case. So it's r multiplied by a multiplied by dz. So it's gonna be f dc equals ra multiplied by dz. Again, if you assume a first order kinetics, then the reaction will take this form, and this is gonna be the shape of the equation. Again, we are gonna end up with a differential equation, and this is what we expect in any distributed parameter system, that the parameters change with the distance. If you have an unsteady state operation, that's gonna be more difficult. It's gonna be partial differential equation in z and in t, so it's gonna be more difficult. And in this case, by solving this equation, you should get a concentration profile, that how the concentration changes with the distance. So there should be a concentration profile along the length of the reactor. You should include again the energy balance equation. And in this case, you have to take into account that there is a change of temperature with the length. And again, you need to solve you have this dc by dz, and there will be a dt by dz, which is the change of temperature with the length of the reactor. And they have to be solved, coupled and solved together simultaneously. So you cannot solve this by itself and then solve the other by itself. And again, this is how the calculations go, and how it is tough to deal with these kind of equations. In the gas phase reactions, you should have one more equation, which is the change of pressure with the distance, because the change in composition will result in change in the partial pressures and will result in change in total pressure. So this is one more parameter that you should take into account, and one more equation that you should put in or solve with these equations. So this is how we deal with this kind of equation. Again, I just want to, or the audiences to appreciate what the software does. It will end up with few clicks and few inputs, and then everything will be solved. But it's not as easy as it looks. It's tough. And if you try to write the code by yourself using any software to do the solution, you would understand what I mean. The last type of reactor is the batch reactor. In this case, it's kind of like the CSTR, with the difference that there is no input and no output continuously. Of course, there is input and output, but there is not a continuous input and continuous output. And the reactants are left in the reactor for some time until the reaction proceeds and ends. And this is an unsteady state. Sorry, this is an unsteady state reactor. So in this case, you have to have a d by dt term, and this is how the equation goes. I think there's something wrong here. This should go here, and this should. I'm sorry about this mistake. So this is how the reactor equation will end up with. So it's going to be dc by dt equals negative r multiplied by v, and again I have this term r here, which is the reactor, the reactive reaction, which includes the reaction kinetics. And then you should integrate it for the time, and then you should have a concentration profile over time, not over distance as in the PFR. Now let's see what kind of reactors we have in Aspen Plus. We have these three modules: the CSTR, the RCSTR, which is the rigorously stirred tank reactor. You see that all these have the rigorous term. Because the rigorous term means that it's like what we did in the heat exchangers before. You can do it as a shortcut calculations or in the rigorous mode. So this is the rigorous mode. It's doing this step by step until it gets all the outputs. It's based on the assumption of perfect mixing. This is what we mentioned before. The reactor has the same composition of the product stream. Again, we mentioned this. It can handle kinetic and equilibrium reactions. And we will talk about the reactions later. And this rigorously tubular reactor with or without packaging. So in this case, you can assume that there is a catalyst or no, based on what you need. It assumes perfect mixing in the radial direction, and that there is no mixing in the axial direction. These are the assumptions we mentioned before. It enables the inclusion of coolant, which flows countercurrent or in parallel. So in this case, you can add cooling medium, either like coils or jacket or whatever, and it requires knowledge of kinetics of the reaction. And this is what I mentioned before. The R batch, it is the batch reaction. The kinetic information must be known, so you have to provide the kinetics of the reaction. In this case, you can assume what the definition of the batch is that the product is not continuous. So the feed can be continuous, but the product must be not continuous. It kind of requires some of programming. I'm not sure if we're going to cover this in our series or not, but this is something I would look into in the future. So I'll stop here. In the next video, inshallah, we'll see what we mean by the kinetics and how we can define them in Aspen Plus. So I'll see you then, inshallah. Goodbye.